Inside a raw semiconductor, you have an environment defined by thermodynamic chaos. To build functional technology, engineers must force these particles into predictable, geometric arrangements. The precise spatial distribution of these fixed and mobile charges creates the hidden architecture of modern electronics. The central challenge is calculating exactly how these microscopic arrangements translate into macroscopic, measurable voltages. That relationship is defined by Poisson's equation. It acts as the mathematical bridge connecting the quantum realm of charge to the macroscopic world of engineered devices. Applying this equation requires following a rigid sequence of physical causality. Device physicists use this four-step sequence to determine how a device will operate. The process begins here, determining the exact location and density of localized charge within the material. Because charge exerts force over distance, this density profile generates a specific electric field. Integrating that force builds the electrostatic potential, a voltage-like energy landscape. This potential physically warps particle energy levels, resulting in band bending. Navigating this sequence allows us to establish the electrostatic baseline required to analyze modern semiconductors. We can break down the one-dimensional version of Poisson's equation to see its physical meaning. On the left, we find the second spatial derivative of the electrostatic potential. A second derivative represents curvature. In this context, it tells us that charge density creates curvature in the potential landscape rather than a straight slope. This clarifies a common misconception. Poisson's equation provides potential curvature, not the electric field. To find the field, you must take the first derivative. The right side of the equation represents the physical sources of that curvature. In a semiconductor, these are the four components of net charge. This charge is a balance between mobile carriers, electrons and holes, and fixed ions, known as donors and acceptors. Wherever a localized net imbalance exists among these four foundational components, the entire electrostatic landscape must physically curve to compensate. Mapping this potential to the energy of an electron requires accounting for an inverse relationship. These side-by-side graphs compare electrostatic potential on the left to electron energy on the right. On the potential graph, a positive slope represents a force pushing a negative electron backward. On the energy graph, that same force makes the electron roll downhill toward lower energy. As these equations show, the energy bands shift by -q times the potential. Because electrons carry a negative charge, a positive increase in potential physically lowers their energy levels. Band diagrams are, in effect, upside-down potential maps. Applying these rules to real devices reveals a mathematical dependency that complicates the solution. Potential curvature depends on charge, but the concentration of mobile carriers depends exponentially on that same potential. This creates a circular dependency loop. Because potential and charge are exponentially coupled, finding an exact analytical solution is often impossible. To bypass this, engineers use the depletion approximation. By assuming mobile carriers are absent in high field regions, the charge density becomes a fixed constant that is easily integrated. This approximation allows us to model complex devices with a manageable level of mathematical precision. This six-step algorithm provides a methodology for extracting measurable values from a device cross-section. If we analyze a slice of depleted N-type material, we assume a constant positive charge density. Integrating this constant once yields a linear electric field profile. Calculus requires us to solve for constants of integration using the material's physical properties. We solve for these using boundary conditions, which serve as physical anchor points for the math. In a neutral bulk region, for instance, the electric field must drop to zero. Combining integration with these boundary rules converts abstract charge into specific, measurable field gradients. This identical sequence of operations forms the underlying geometry for a wide range of technologies. In a PN diode, potential curvature determines the exact physical width of the depletion region. In Schottky contacts, it dictates the triangular electric field profile that governs the breakdown voltage. It even defines the threshold voltage required to activate a modern MOSFET. Poisson's equation serves as the architectural blueprint for device engineering, linking microscopic charge distributions to the macroscopic behavior of the digital world.